So it will be for a large part on ALD, but also a little bit about MLD. And so I will discuss the different approaches that exist for area-selective deposition, but I will also try to start a discussion on how we can maybe use MLD technology for enabling or improving area-selective deposition. So area-selective deposition is about bottom-up fabrication. So as you know, in nanotechnology, we basically have two flavors of making materials. We have top-down and bottom-up. And here I make a comparison to building technology to introduce this to you. So in building technology, people realized thousands of years ago that if you start with a solid rock and you remove the material that you don't need, then basically the options that you have are quite limited. So basically it's easier to work with smaller building blocks like bricks, and then you can basically make the materials or the buildings that you need. So the interesting thing is that in semiconductor fabrication, so here we're talking about making computer chips that go into your laptop or smartphone. In semiconductor fabrication, we haven't gone through such a transition yet. So semiconductor fabrication nowadays relies almost completely on top-down processing. But the thing is that now we're facing some challenges that require the implementation of at least some bottom-up processing steps. So that's the topic of, one of the topics of this presentation. So what is area-selective deposition, or area-selective ALD in this case? So here I show some examples of structures that were made, in my opinion, with area-selective deposition. So you can, for example, think about patterning a resist film to basically limit the growth to specific locations. So we'll talk about extensively, especially in the first part of this talk. This is another example. So this is about selectively coating a nanoparticle to make a core shell nanoparticle. And this is, of course, for example, interesting for catalysis applications. This is an example from the literature where they have done ALD, and in this case it turned out to be selective to the grain boundaries or the edges of highly ordered graphite. So basically you can tune your process such that only the growth occurs there. And you can imagine that also the fusion phenomenon play a role here, as we have heard in the previous talk. This is another example where the growth occurs selectively at the side walls of a trench, which also qualifies as area-selective deposition. And this is another example. So here in this case, I think it's a little bit difficult to see, but here in this example, they managed to make the growth selective to certain facets of a nanoparticle. And you can imagine that this is also interesting for catalysis applications. So taken together, we can describe this as bottom-up fabrication by deposition of atoms at specific locations. So we're using here atoms as building blocks in the same way as in the building technology you use bricks. And in a way this addresses a long-held dream in the field of nanotechnology. You can, for example, think about the famous lecture of Richard Feynman, There's Plenty of Room at the Bottom. So this was in the 1950s. So he said there, what could we do with layered structures with just the right layers? With this description, I'm already thinking about atomic layer deposition or molecular layer deposition. And then he continued, what would the properties of materials be if we could rearrange the atoms the way we want them? So here this is about depositing the atoms where you want them. And so this is, with area-selective deposition, we're making a step towards this condition. By the way, please feel free to interrupt me when you have questions. I hope this can be kind of an interactive thing. But we'll see about that later on. So then the next thing to point out is that basically there are two flavors of area-selective deposition. So most of the early work heavily relied on patterning. So there are many area-selective ALD approaches that involve certain patterning steps. So that's something that I will especially discuss in the first part of this presentation. But recent interest is actually about a different thing. So the recent interest there, I described this here as area-selective ALD on a device structure. So here we're considering a case that we already have done patterning, and you have maybe like a partially processed device structure, so you're somewhere halfway your fabrication process, for example, of a transistor. And the idea is that instead of doing lithography for every layer, doing patterning for every layer, what you do is selectively make use of the fact that there are different materials are present, and then selectively grow on only one of those materials. So if you then do this, apply this material bottom up, then you can simplify your fabrication process. So this, we'll talk about that, especially in the second part of this presentation. But what I want to mention here already is that this is currently one of the main motivations for why there's the attention in area-selective deposition is increasing in recent years. So this is summarizes the aim of this presentation. So first I want to introduce you to area-selective ALD and MLD by discussing various approaches that have been reported in the literature. I will motivate why there's interest in area-selective deposition in more detail than what I did so far. But the third thing is also I want to stimulate your creativity to design area-selective deposition approaches based on MLD technology. So I tried to include a few discussion topics, and maybe we can see if there are some things we can do by combining area-selective deposition and MLD technology, and see if we can make a step further there. So this is then the outline. So the first part, as said, will be mostly about patterning. And then, so here, I will first start with an introduction to patterning, and then discuss how you can basically pattern ALD chrome films and how that's related to area-selective deposition. In the second part, there we'll talk about this second flavor of area-selective ALD, which I described as area-selective ALD on a device structure. But this part will also enlarge mostly about how can we make a process selective. So as you know, if you do ALD or MLD, typically what you have, the situation is that you coat the entire surface uniformly. But here we want to limit that growth to a specific location. So how do we change the chemistry of this process such that it only occurs at certain locations? And then at the end I will discuss the challenges in this field, and there I also want to address if we can maybe make use of MLD technology. Okay. I would like to start with briefly going over conventional patterning, and I think this should be very familiar to many of you, but I think it's good to use this as a starting point, maybe to refresh your mind, or at least make sure that we're all on the same page. So the question here is, if we start, for example, with a silicon substrate, how can we make pattern structures on top here? So let's briefly go over that. So what you typically do is first deposit your film. So this could be ALD, this could be MLD, but also evaporation or sputtering. It doesn't matter for this example. And then what you typically do is you spin coat a resist on that. So the wafer rotates, and then you drop cast a solution. So that's typically some molecules in a solution, so you can typically have to do a step to evaporate the liquid. And then the most important step is the patterning itself. So that is typically done using, at least if you talk about high volume production, with photolithography. So how does that work? Well, you typically use a mask, and then you expose, you shine light through that mask, and in that way you expose this resist film locally to this UV light. And then as a result of this local exposure, you get a chemical change of your resist film. And then the next step is that you're going to develop this resist. So you basically put it in a solution, and then if you use a negative resist, then basically this will dissolve, and then what you have left is the patterned resist. Then the next step is to do etching. So basically you want to transfer this resist pattern to your underlying film. So what you can, for example, do is anisotropic etching using a plasma. And then the last step is to strip the resist, which can also be, for example, done with a plasma. So basically a series of steps to define those features. And we can summarize it like this. So we first, so these are the main steps. So we first deposit the film, then we pattern the resist, etching, and then you strip the resist. So this is the most basic approach. There's another conventional approach, which we refer to as lift-off. And that's basically kind of the other way around. So here in this case, you pattern the resist film first before you do the deposition. And then in this step, this is the actual lift-off step, you dissolve the resist and then you remove this resist together with the material that's present on top. So in that way, what's left behind is the same thing, the structure. Do you have any idea why this could be beneficial as compared to etching? Don't be shy, just shout. Still early. Okay. So I think there are two main reasons. So one thing is if you work with sensitive materials on which you cannot use etching chemicals, then this can be a milder way of doing this. Another thing is that this approach works better if you're processing materials that are difficult to etch. So if you think about materials like gold or platinum, you need very strong chemicals to etch that, so then it's often better to use this lift-off approach. Okay, so this is about conventional patterning very briefly, but let's now discuss area-selective deposition. And I would like to start here with the most standard approach for area-selective deposition, and that is to make use of self-assembled monolayers. So self-assembled monolayers are monolayers consisting of molecules like this. So this is a monomer where you have a head group that facilitates the binding to the surface. So here you can see some different head groups, which basically determine on which material these molecules absorb. Then the important thing is that you have this long alkane chain, and the van der Waals interaction between these chains makes sure you have a very ordered monolayer. That's very important for making the process selective. And another thing is that you have the end we call the tail group. And basically what you do is you functionalize your surface with these molecules. And so if you, for example, start on an oxide surface, then in the beginning you have hydroxyl groups present. But if you apply these molecules, then you end up with a surface that is functionalized. Well, basically the chemical nature of the surface is determined by these tail groups. And if you have, for example, something like CF3 or CH3 tail groups, then these are relatively unreactive. So if you then come in with a precursor, then this precursor shouldn't absorb easily on the surface. So that's what you can use to do area-selective deposition. So let's look at an example. So here in this example, the goal was to do area-selective deposition of cobalt. And what they did here is they used conventional patterning or lithography to pattern a resist layer. And then they dipped this sample in a solution containing these molecules, octadecyl trichlorosilane. So also these are these long chain molecules that I just described. So how you prepare such a self-assembled monolayer, I forgot to mention that, is basically you typically use wet chemistry. So you put the sample in solution, and then you have to wait until an ordered monolayer forms. And this in practice that can take a long time because, well, the molecules have to rearrange and you have to make sure that they are nicely ordered. So typical times is often something like soaking it in a solution for a day or something of that order. So here they dipped it in a solution and then they stripped this resist film. So the result is you have a patterned self-assembled monolayer, and then they performed the deposition. And here, as I just explained, the surface is terminated with these CH3 groups. So if you then come in with the precursor, then the precursor doesn't want to adsorb at that surface. And as a result of that, you get selective deposition at those regions where the self-assembled monolayers are not present. And then, what I didn't draw here is, but you can also strip then the self-assembled monolayer, and then the end result is the pattern. And here you can see some of the results. So this is just after functionalization of the surface. And this is after ALD. You can see that only cobalt is present at specific regions. Okay, let's discuss a little bit more how this works. So how do these self-assembled monolayers make sure that you don't get deposition? So what is the mechanism of that? So basically, the role of the self-assembled monolayer is twofold. As you have learned earlier in this workshop, ALD, MLD chemistry typically starts at certain functional surface groups. Think, for example, about hydroxyl groups at your surface. So one thing you can make use of here is that these self-assembled monolayer monomers might adsorb on hydroxyl groups, and then if they have reacted, then of course they're not available anymore for the precursor. So that's one thing, remove the hydroxyl groups from the surface. Then the other thing is that if the van der Waals interaction does a job, then you should have a nicely ordered monolayer. And that means that, if you come in with a precursor molecule, then in principle you have this physical barrier that prevents the precursor from reaching the substrate itself. And if it cannot reach that interface, then of course it also cannot lead to deposition there. So that's, these are the two main reasons why a self-assembled monolayer can deactivate the growth. And this is important because we'll come back to this later in the discussion as well. In practice, it's a little bit more difficult. As I mentioned, typically forming a self-assembled monolayer can take a day. And if this monolayer is not perfect, then you might have some pinholes. And these are sites where the precursor can basically interact or attack this surface. And another thing is that these molecules are not always very thermally stable. So many self-assembled monolayers, they already dissolve or degrade at temperatures above 100 degrees. So if you want to do your ALD process between 100 and 400 degrees, then you may have some desorption of these molecules during our deposition. So in practice, what you always get is that maybe you block the growth for a while, but at some point it will start. But at some point you will lose your selectivity and also grow on the surfaces on which you don't want to grow. So as I said, this is one of the most standard ways of doing area-selective deposition, which also means that it's quite well studied. So here, this is a study where they tried hafnium oxide ALD on a surface functionalized with self-assembled monolayers of different lengths. So there at the x-axis you have the number of carbon atoms in this alkane chain. And what you can see is that, well, first of all, the red is the water contact angle. So this says something about how hydrophobic the surface is. So the more hydrophobic, the lower the chances that the precursor can react with the surface. So you can see that it's more hydrophobic for like above 10. Then this is the thickness. So this is basically the thickness of the self-assembled monolayer. You can imagine that this should scale with carbon length. And then the line in black is the percentage of hafnium after deposition. And you can see that this drops down to 0 after, if you use a self-assembled monolayer of at least 12 carbon atoms. So it seems that you need a certain length of the self-assembled monolayer to deactivate the growth. And basically this is because the longer this chain is, the better this van der Waals interaction between these chains, and then you have a better chance of forming a nicely ordered monolayer. And you may have noticed that this looks a little bit similar to what you have, but it's a little bit similar to an MLD film. So maybe this is a good way of starting a discussion on this. So the question is here, what are the similarities and differences between such a self-assembled monolayer monomer and what you can, for example, grow with MLD? And then the follow-up question is, can we use MLD films in a similar way to deactivate the ALD growth? So what I would like to ask you is to have a short discussion with your neighbor maybe, and then we can have later on see if we can come to some new conclusions. I should note that I'm not an expert on MLD myself, so I hope to learn something here. And if you are just started in this program for like 1 or 2 weeks ago, you might know already more about this than me. So this is, let's see how this works. You shouldn't be too shy to talk to your neighbor. Then we have a problem for this network. Okay, let's discuss this. So what do we need if you want to deactivate growth? What's your conclusion in this?
We need to deactivate?
Yeah, so what's so what if you, let's say you want to use an MLD film to deactivate the growth, so what are the elements that we need to make sure that the ALD growth doesn't stop?
The ALD growth doesn't react with this function.
Yeah, so indeed, the important thing is that your film doesn't react with the molecules. So what do we need for that?
Repulsion between.
Excuse me?
Maybe any kind of repulsion between the.
Yeah. So one thing is that we have these different monomers, And of course, an MLD film is designed such that if you apply a monomer, then it should be reactive to the next one. So what do we need at the end? That's maybe the first thing I should ask. Nothing. So what is nothing?
No reactive site.
Yeah, so what is that? If we think about molecules that we could use for MLD. So typically you have a bifunctional monomer, but you need something with only one functional group, and then you can put that at the end maybe. So that could be a starting point. Anything else?
Yeah, like for example, we can go normal MLD and then modify, introduce extra step, modify the M groups so that they're not reactive anymore. For example, if they're alcohol groups, we can just introduce, convert them to SAM.
Yeah, that's indeed. So that's something we should think about. So doing first a few MLD layers, and then at some point do like a termination step such that you don't have anything at the end. So if you think about the SAM monolayers, what were the mechanism how we deactivated the growth? I mentioned two things. You remember that? So first, you should react with hydroxyl groups. Oh, that's good. That should happen already in step one. The second thing was, you remember that? Anyone here in the back? So you need like a nicely ordered monolayer. And I also showed you that you need a certain length. So what do we need to do there? Yeah, so you can do like a few cycles to make sure that it's long enough and that you have like a nicely ordered monolayer. Do you think this will work, or are there any limitations? Maybe I should look at the more senior table here. I have my doubts myself.
It might work, but it looks so complicated.
Yeah, so I think one of the limitations is, well, the nice thing about these SAM monolayers, if it's like one molecule, and if it's ordered, then only this thing is reactive, that reacts to the surface, and the rest is kind of inert to your ALD chemistry. If you think about this, making a layers, coupling these MLD precursors until you have a certain length, then I think this only works if it's like a perfect layer. So if you, for example, in your last step, you're not completely in saturation, or you don't have like a nicely, so there might be some secondary reactions where you don't cap every monolayer, and of course every point where it's not perfect is a site where you can adsorb your precursor. So I think one of the benefits is this molecule is very good for this, in the sense that this thing shouldn't react with most ALD precursors. And here, if you do the entire layer, then you have a lot of sites where if it's not perfect, then there your growth will start. Any questions on this? Okay. So then the next thing is, so I gave an example on area-selective ALD, but this is something similar has also been done for MLD. So this is something that has been reported for MLD of polyuria using this chemistry. And here in this case, they demonstrated that if you do this chemistry on silicon oxide, then you get the linear growth that you expect from most MLD chemistries. And if you functionalize your surface with these ODTS, self-SAM monolayer, then you can at least deactivate the growth for at least something like 30 cycles. And here in this study, they used a different patterning approach to deactivate the surface with self-SAM monolayer. So this is micro-contact printing, also known as soft lithography. So basically you use a stamp, and you put this in a solution, and then you stamp this solution containing these self-SAM monolayer monomers on the surface. So then you have a pattern with self-SAM monolayers, and then you can perform deposition, and that's what they did here. So here they performed this MLD chemistry, and so this is an SEM image, this is a Auger map, And I think here the white means that nitrogen is present, which is present in this MLD chemistry. So in that way, you can see that if you apply your self-assembled monolayers here with the stamp, then you can have selective deposition at the rest of your surface. So schematically, it looks like this. So you start with a wafer. You use some technique to pattern the self-assembled monolayer, and then you perform your deposition. And then the idea is that the growth occurs selectively only there where the self-assembled monolayer is not present. So this approach we refer to as area-selective ALD by area deactivation. So you locally deactivate your surface towards ALD. So how does this compare to the conventional patterning steps I explained earlier on? So here we talked about these two conventional techniques, and what you see is that area-selective ALD by area deactivation is very similar to the lift-off approach. So in both cases, you start with patterning, then you do your deposition. But the main difference is that with the lift-off approach, you deposit on your resist, and then you remove it afterwards. And here, what we aim for is that the deposition doesn't occur on the self-assembled monolayer, so only where the self-assembled monolayer is not present. So then, the question you may ask is, why is this interesting to do? So what is the benefit of using area-selective deposition instead of these conventional techniques? Well, one thing to realize is that conventional patterning consists of many, many process steps. So I showed here the four main things, but you should also realize that, for example, the patterning itself are a few different steps. So you can do the patterning with different techniques. We talked about photolithography, we talked about soft lithography, but also you can think about E-beam or imprint lithography. Not going into details there, but the bottom line is here is that you have many, many process steps. And what the problem is that some of these process steps may cause compatibility issues with the materials that you're using. And to illustrate what I mean with these compatibility issues, I want to give an example from our own work. So let's say that we want to make a device like this. So this is a carbon nanotube field effect transistor. So if you want to make this, then you have to pattern these electrical contacts on the carbon nanotube. And then if you want to do this, and you want to design a process flow for that, then you have to consider that these are very sensitive materials. First of all, since it's a sensitive material, you cannot use most etching chemistries, because you would simply damage the surface of this fragile thing. The other thing is that the carbon nanotube has a relatively inert surface, so if you do pattern a metal on top, then the interaction between the metal and the carbon is not very strong. The adhesion is very poor. So if you use a lift-off approach, then basically what often happens is that you get delamination of your contact. So you lose basically your device yield. Then on top of that, you actually even don't want to use a resist film, because the resist, that's typically a hydrocarbon, so that's carbon on carbon, it sticks very well, and it's basically almost impossible to remove this resist film without damaging your carbon nanotube. So here you see the result of a related study. So this is on graphene, as you know, a very similar material. And here we used all the tricks in the books to clean the graphene, and at the end, you still have some residue there. So making clean devices using resist films is very difficult to do. So what we basically need is a completely bottom-up approach to do this. So what we worked on is a technique like this. So it's a two-step approach. So what we basically did is we combined ALD with another deposition technique called electron beam induced deposition. So what you do with this technique is you use a precursor, and then you dissociate that precursor with electron beam. And this precursor could be very similar to what you use in ALD. So this is done in a vacuum system, an electron microscope. You dose this precursor, the precursor adsorbs, and then you scan the electron beam over the surface. And then locally, where you have the interaction of the electron beam with the precursor, there you get some deposition. In principle, it looks very nice. You can focus the spot of the electron beam into like 1 nanometer, so you can go to very high resolutions. But in practice, what you have is that the material that you deposit is of a very poor quality. So for this application, we worked on platinum. So for platinum, we get a purity of about 15 atomic percent, so 1.5. And you can imagine that this is not really what you want for the application if you want to make contacts. So what we do here is basically we make a very thin seed layer with this EBID technique, and then we switch to ALD, and then we selectively deposit on this seed layer. And I'll come back later to the details of how we can make sure that this process only occurs on the seed layer. But basically what we do is by combining this patterning capability of this first technique with the material quality of ALD, you can make high quality contacts. So the seed layer thickness is here about half a nanometer, or like a monolayer of material, that order of magnitude. That's enough to start the growth. So we'll come back to the chemistry later. So this is to show this approach works. So this is a carbon nanotube field effect transistor. It's almost impossible to see the carbon nanotube here. But this is a graphene-based device. So here you see a strip of graphene with the electrical contacts on top of that. And the nice thing about these structures is that they were made without etching, without lift-off, even without using any resist films. So completely bottom-up. So what you may have noticed that this approach is quite different from using self-assembly monolayers. So it's actually the other way around. So what we do is you pattern a seed layer, and then you locally activate your growth, and then you selectively grow on this activated layer. So this approach we refer to as area-selective ALD by area activation. So it's the other way around as compared to the first approach. So then this is the overview of the different patterning approaches we have discussed. So at the left, we use top-down or subtractive processing. So here you remove material using etching or lift-off. And here, towards the right, it's more bottom-up. And here for the area deactivation approach, there's still one subtractive step. You have to remove the self-assembled monolayer afterwards. But this area activation approach could classify as completely bottom-up. Okay. Any questions, feelings, thoughts at this stage? As said, please feel free to interrupt me. So this was the first part. But
There was a question.
One question.
sorry, I didn't see that.
I wanted to know the scale of this, the positions that you do, how small they are.
Yeah, so this example, I have to remember this. I think this is about between 50 and 100 nanometer in width. And in principle, with the E-beam, you should be able to go to like 10 nanometers. We also did some demonstrations of that, but then with the E-beam, it's also challenging to make two contacts next to each other that they don't influence each other. But yeah, so a related question about this might be, if you do deposition, do you only grow in the vertical direction or also in the lateral? That's the typical question with area-selective ALD. I'll come back to that at the end. So that's one of the challenges that we're currently facing. Any other questions? Okay. So what we discussed so far is kind of the PowerPoint version of area-selective deposition, where everything looks nicely and ordered. In practice, if you do patterning, you have to, you're facing all kind of challenges, especially if you go to small dimensions. So you can think about if you define a line with lithography, that in principle what you get in the end is not a perfect line, but you get some line edge roughness. You can have that the resist film that you make may not, well, you have to think about the structural integrity of that film, so it may collapse during your development. But a very important challenge these days is in the alignment. So if you make a multi-layer device stack, how do you make sure that all these films are present at exactly the right spot? So that's one of the challenges where area-selective deposition can help. And then we're talking about this second flavor of area-selective deposition, which I described as area-selective ALD on a device structure. So that's what we're going to talk about now. So that's the second part of this presentation. And in this part I will also go into more details about how you can make a process selective. So we talked about, for example, these platinum contacts. How do we make sure that the growth only occurs in the seed layer and not on the rest of the substrate? Or how does the self-assembled monolayer deactivate it in detail? So, yeah, alignment. So the first one to talk about the challenge of alignment at the nanoscale. And this is currently one of the main motivations for why there's currently a lot of interest for area-selective deposition. So let's go over that in a little bit more detail. So let's say that you want to make a structure like this. So this could be like a barrier layer or interconnect. It doesn't matter for this example. But let's say that we want to apply this green material only on top of the orange, not on the blue. So what you would do conventionally, we already have discussed that, is you deposit your film, you do patterning with lithography, and then you etch. Well, this looks very nice in PowerPoint. But in practice, especially if you go to smaller dimensions, then you also have to think about the alignment of the features. So do you have any idea for how small features are in state-of-the-art computer chips these days? Just shout. Is that like micrometers, nanometers, hundreds of nanometers?
They say, for example, 10 nanometer lithography. I think that is the size of the...
Yeah, so we're at the 7 nanometer node, which means that some of the structures in these computer chips should be around that dimension. So this is what you typically call the critical dimension. And then in practice, if you want to make a reliable device, what people say is that the error in the alignment, what people refer to as the edge placement error, can only be like a quarter of this critical dimension. So which means that if you want to make something of 7 nanometer, this is maybe like 1.5 nanometers, like 10 atoms wide. So you can imagine that this is becoming extremely challenging for these small dimensions. So the challenge in downscaling of electronics is nowadays not only about making smaller features, but the alignment is becoming one of the main bottlenecks. So the alternative is, and you see this one coming, is to selectively deposit the green on top of the orange. And then if you do that, then you can get away with using fewer lithography and etching steps. You basically eliminate this alignment issue. And then we get something that we refer to as a self-aligned fabrication scheme. So self-aligned fabrication, that's currently the main reason to work on area-selective deposition. So let's look at an example. So this is cross-section. These are cross-sections of computer chips at the interconnect level, so the back end of line. So typically, so the transistors should be present at this level, but then you need to wire these devices together. So these are multiple levels of all kinds of connections. So this is typically copper these days. We're moving toward cobalt. And then, so here the devices are wired together, but also to the outside world. And you can see that, well, you have something like 10 different layers on top of each other. And in principle, for each layer, you should do lithography, etching, and all those steps that we discussed before. So in each time, for each new layer, you have to think about the alignment relative to the layer below it. And so this looks very nice. This is a cross-section of the X-point memories. It's a relatively new memory. Here you can see that it's actually not all that nice. Some of them are not so well aligned. And this becomes even worse if you have to consider that if you want to make small features, then typically it's not just one mesh that you use during lithography. No, you typically have like 3, 4, 5 different masks, and they all have to be aligned relative to each other. In some companies in the semiconductor industry, they call this the web of pain. So basically aligning one layer on top of the other, and with more and more complex devices, it becomes a nightmare. So let's look at one specific applications. So these vertical connections are called vias. And so what you basically want is that if you do the patterning of this via, that it nicely lands at the right spot. But in practice, as we have just discussed, you get an edge placement error, EPE. Here you can see an example of where it goes wrong. So here are two vias next to each other, and you see that the one touches the other. And the result of that is that you can have a short. So there are like order of magnitude 10 million vias in a computer chip. At the higher level, it's maybe a little bit less critical, but at the lower levels, if you have a misalignment, that might mean that your entire chip doesn't work. So it's extremely critical to do it as well. So how can we solve this? Well, you could think about maybe selectively growing this copper via. In practice, that will be very difficult because of the aspect ratio of the structure. Come back to that later. But the solution that people are considering or working on at the moment is to selectively grow a barrier layer here. So here, the yellow is copper, the blue is a dielectric. So what we want to do here is selective deposition of a dielectric on a dielectric without coating this copper. And if you have an ALD process for that, you can grow this barrier layer, and then even if you pattern this via at exactly the right spot, the same spot as with the EPE as before, you have this additional spacing that prevents the device from shortening. So this is basically by adding one selective deposition step, you can make this device more reliable. Is that clear? Okay. So how do we design a process for this? So how do we make sure that the deposition is selective? So in contrast to what we discussed in the beginning, so no, we're not really talking about patterning itself, but we're considering that we have a device structure with different materials present, and the aim is to selectively deposit on only one of those materials. So what we typically define is a growth area and a non-growth area. So the growth area is the material on which we do want to grow the material, and the non-growth area, there we don't want to see any deposition. So the example of the self-aligned fabrication of interconnects of the last slide, then the dielectric is a growth area, and the copper, on which we don't want to grow, is the non-growth area. So what we're looking for is something like this. So what we would like to see is that we have maybe immediate growth on this growth area, and maybe it takes a while before the growth starts on the non-growth area. So if you have a certain nucleation delay before the growth starts, then we can make use of that to have selective deposition on the growth area. So how can we make a process selective? Well, one thing you can do is if you have different materials present, then, for example, if one material has hydroxyl groups, maybe the other one is hydrogen terminated, then you might be able to use that difference in surface chemistry to have selective adsorption of your precursor. So that's the first approach, selective precursor adsorption. So this is an example from the literature. So this is a study by the group of Yves Chabal. So they looked at hydroxyl terminated versus a hydrogen terminated silicon surface, and then performed thermal ALD cycles using water as the co-reactant for different precursors. So this is what you see here. These are the results from XPS. What you see here is if you use this dichloride precursor, then it adsorbs or reacts on the hydroxyl terminated surface, but you don't see anything after 10 cycles on the hydrogen terminated surface. So in other words, you get selective deposition on the hydroxyl terminated surface. Then here the hafnium is the other extreme case. So basically you get almost the same deposition on both of the surfaces, and the alumina is a little bit in between. So there you get deposition on both surfaces, but it's more on the hydroxyl terminated surface. So here this would mean that maybe the growth started, but maybe after a short nucleation delay. So in this study they tried to explain this by studying the underlying surface chemistry using density functional theory calculations. So from that they learned that the adsorption of these precursors on these different hydrogen terminated surfaces in all cases is quite, the barrier for that is quite high, but the reaction is especially the most difficult on this surface, for the dichloride precursors. So what we learned from this study is that for some precursors you can design a selective ALD process by just exploiting differences in surface chemistry. But also for some other precursors it doesn't work that well. Then the other thing I want to mention here is that this type of approach where you have a difference in precursor adsorption typically works only if you want to grow maybe a few nanometers of film. If you want to make a thicker film, and at some point you get into this situation that at some point the growth starts. And yeah, so that's basically, if you think about an ALD chemistry, you have like, you typically understand the reaction mechanism, but there are always some side reactions that also play a role here. So in this case, some water may, for example, physi-swap on the hydrogen terminated surface, and then you can get kind of a CVD type of reaction where the incoming precursor reacts with this physi-swap water, and then in that way you can create a site for the nucleation to start. So basically, if you want to grow a thicker film with area-selective ALD, the main approach is to use self-assembled monolayers. We already have talked about that before, but one thing that I didn't mention so far is that you can also make use of the fact that many self-assembled monolayer monomers have the property that they selectively adsorb at certain materials. So you don't necessarily have to use patterning if you already have different materials present. So here in this case, there's an example where that shows if you have these ODTS self-assembled monolayers that we talked about earlier, these selectively adsorb on hydroxyl terminated silicon oxide and not on a hydrogen terminated region of the silicon, meaning that if you first functionalize your surface, then you can do area-selective deposition on the hydrogen terminated region. And the other way around, if you use 1-octadecene, that self-assembled monolayer has the property that it adsorbs on the hydrogen terminated region, so then you can do selective deposition on the hydroxyl groups here. So this is then an example from the literature. So here they use, this is also for MLD, by the way, again polyuria. So in this case, they use the sample with hydrogen terminated and silicon oxide hydroxyl terminated regions, and then this octadecyl trichlorosilane, what we just discussed, that adsorbs on the hydroxyl terminated regions, and then you can do MLD selectively on the hydrogen terminated regions. Okay, so we already talked about the mechanism of how self-assembled monolayer deactivates the growth. I showed you this slide before. And what I also mentioned there is that typically at some point you lose your selectivity. And it is because often, because the thermal stability of these self-assembled monolayers is poor, which means that these monomers might dissolve or degrade during the deposition. So one thing you can do is, instead of, well, I also mentioned in the beginning that what you typically do is soak the sample in solution, use wet chemistry. For some more simple self-assembled monolayer, you can also do vapor phase dosing. And then the nice thing is that you can basically repeat that a few times during your deposition. So you can do a few ALD cycles, but then you might lose some of your monomers because they desorb from the surface. What you can do is then redose them again. So basically repair the pinholes in the self-assembly monolayer, and then continue, and then in that way you can make a thicker film in an area-selective manner. So in this case, this is about area-selective ALD of zinc oxide, where they repeated the functionalization step 3 times, and then they also managed to make 3 times thicker films. So then depending on what kind of self-assembly monolayer you use, what kind of ALD chemistry you have, you may have to do this more often. And the extreme case would be to do this every ALD cycle. So then we get a 3-step ALD cycle. So that's the approach that we have explored in our more recent work. So again, we have 2 different surfaces here, the growth area and the non-growth area. So we want to grow selectively on the growth area. So what we do is we dose small molecules that we call inhibitors. And these molecules are relatively small as compared to the self-assembly monolayer monomers, such that we can dose them in short dosing steps, such that we can do this every cycle. Then we have precursor exposure and co-reactant exposure. So these are the normal steps of the ALD cycle. And I want to show you a short video of how this works. And since, as I mentioned in the beginning, area-selective ALD to me is like using atoms as building blocks, which is kind of similar to playing with Lego. So that's the inspiration for this video. Hopefully it works. Yes. Okay, so we're looking here at 2 different regions. The black is the growth area, this is the non-growth area. So the inhibitor, you see that it selectively adsorbs, at least in the Ghent version, on the non-growth area. There we dose the precursor. And the idea is that these inhibitor molecules should block the adsorption of the precursor, such that we only get adsorption of the precursor at the growth area. Then we dose the co-reactant, and the function of this co-reactant is to remove these inhibitor molecules, but also the ligands of the precursor. But the end result is that we have deposited the atoms that we want. And then, of course, we can repeat this over and over again. So inhibitor, precursor, and co-reactant until we have selectively deposited a film on the growth area. So let's go back to this slide. So basically, we have a few different requirements for the different steps. And I will spend a little bit more time on discussing this approach because I think this could be a topic for a next discussion about how maybe we can use something of the MLD toolbox. So the requirements are, for the first step, that we need selective adsorption of the inhibitor on the non-growth area. Then during this step, the inhibitor should block the precursor adsorption such that you only get precursor adsorption on the growth area. And then here in this step, we want to remove the inhibitors together with the ligands of the precursor. So this is a typical result. So this is about area-selective ALD of silicon oxide. So for this we use this 3-step ALD process. So acetyl-acetone, that's our inhibitor. Then we have this diethylamine silane as a precursor, and an oxygen plasma. So this is a plasma-assisted process for doing this. And then what you see here, this is the nucleation behavior of this 3-step process on different starting surfaces. So basically we perform exactly the same recipe on all those different materials. And what you see is that we have a set of materials in which we have immediate growth. So that's silica, silicon nitride, germanium oxide, tungsten oxide. And there are some materials on which it takes a while before the growth starts. So you see, for example, on hafnia, titania, alumina, then it takes 10 to 15 ALD cycles before we see some deposition. And this difference in nucleation behavior we can use to do selective deposition. So for example, we made some patent samples by patenting alumina on germanium oxide. So then we have alumina and germanium oxide on the same sample. And what you then expect is that it only grows, if you do like, let's say 15 ALD cycles, you grow on the germanium oxide, so that's the blue here, but not on the aluminum oxide, that's the red here. So this is then the result we get. So here this is a result of TOF-SIMS mapping. And what you see is that the silica has basically the same pattern as the germanium, and the aluminum is the opposite pattern. Or in other words, the silicon is present in the germanium regions and not on the alumina. So this demonstrates that we have selective deposition. Okay, so let's look a little bit more detail on how this works. So the data I showed here, this is basically, this was measured with spectroscopic densitometry, where we do a measurement after every cycle. But then we also did some experiments where we did a measurement after every pulse. And that gives you some insight on the mechanism of what happens. And I realized that there's a lot of information in here, so we'll do this a little bit step by step. So we're looking here at two different starting surfaces, alumina and silicon oxide. So the alumina represents the surfaces on which we had a nucleation delay, and the silica represents the surfaces on which we had immediate growth. That's of course also the material that we're growing. So what you see is that, well, we do here 3 different ALD cycles. So we do AC, ABC, and BC cycles. So AC would mean that we alternate between the inhibitor and the plasma, the co-reactant. So here what you see on the alumina, if we dose the inhibitor, we see adsorption. And then if we do the plasma, then we remove the inhibitor again. So this tells us that the inhibitor adsorbed and it's reversible adsorption. If we do exactly the same pulse on the silica, we don't see much happening. Or in other words, this tells us that the inhibitor is not able to adsorb on the silica. Or in other words, we have selective inhibitor adsorption. So that was one of the requirements. So that seems to work. Then here, these are the ABC cycles, so the full 3-step process. What you see then is if you dose the inhibitor, adsorbs, that we already saw here. But then if you dose the precursor after that, then we don't really see a change. And this tells us that the inhibitor is apparently able to block the precursor adsorption. So that was requirement number 2. And then with the plasma, remove the inhibitor again. So effectively here on this aluminum oxide, we don't see anything happening. Then on the silica, there we don't get inhibitor adsorption. So the increase here, that's the precursor adsorption. And then with the plasma, we remove the ligands of the precursor, but the end result here is that we get deposition, which is actually the same as what we get if we do the normal BC cycles. So taken together, what we learned is that we have selective adsorption of the inhibitor on the alumina, and also that the inhibitor is able to block the precursor adsorption. How does this, to study this selective adsorption of the inhibitor, we also did some density functional theory calculations. And what we see is basically that the adsorption of the inhibitor on this surface is, on the alumina, is very favorable, but on the silica it has a high barrier and it's also thermodynamically unfavorable. So that's why it doesn't happen on that surface. But that's one thing I want to point out, and that's interesting for the following discussion, is that here the inhibitor is this molecule. So we have here 2 oxygen atoms, and it apparently adsorbs on the surface by bonding to both of its oxygens. So this is called as a bidentate configuration or a chelate configuration. So that's important because then both of these reaction groups are pointing toward the surface, and you have like an unreactive thing at the top. And that's, I think, part of the reason why this molecule can deactivate the ALD growth. And that brings me then to the next discussion. So can we use the toolbox of molecules that we use in MLD maybe as inhibitors for such a 3-step area-selective ALD process? So here I took this from the literature. So in MLD you have molecules to stimulate the growth, you have bifunctional precursors, you have monofunctional precursors, etc. So what could you use here to make the surface to deactivate the growth towards the ALD? So maybe take a break again a few minutes and discuss with your neighbor.
Antes is ook gebruikt. Ik lees artikel. Ik goed en ik heb alle vertrouwen gegeven.
Okay, let's continue. Any volunteers? No? Let's see. So, yes, the question is what kind of combination of molecules can we use to make something that might deactivate the growth? Maybe think about what we discussed about some monolayers in the beginning. Come to any conclusions here?
Actually seems to be the same issue, that it's bifunctional.
Yeah. So we also have a monofunctional precursor here, this one. So one thing you can do, so the first requirement for the cell-to-cell monolayers is that you want, if you have functional groups where your precursor can react, is that your cell-to-cell monolayer reacts with this. So we could have something similar here. So that maybe such a monofunctional precursor might react to the hydroxyl groups and then that way deactivate the group. So that's maybe one path. So some of those monofunctional molecules might be useful as an inhibitor. Anything else you can think of? What was the second requirement for the cell-to-cell monolayer?
Well, another strategy could be a heterolytic instead of like for bifunctional molecules. So one should be attaching to the surface and one should not be reacting on the next cycle.
Yeah, but the problem is if you use something like this, then you have like a reactive group at the top. So what's the solution to that? Actually, we already talked about this.
Yeah, extra step.
Captain.
Yeah, so you can do like a combination of two things. And then, yeah, if you want to kind of mimic what you have with the cell-to-cell monolayer, then maybe you need something with a certain length, and that's actually what we discussed before. So you may want to have some van der Waals interaction between these molecules so you get nice ordering. Anything else? I'm looking at the people from Ghent because I found some inspiration in one of the papers from them. No? So what you could also make use of the fact is that you have double reactions. So if you have a bifunctional precursor and you have a double reaction with the surface, that kind of resembles the configuration we have with acetylacetone on the surface. That basically both of its functional groups adsorb at the surface and then you have something unreactive at the top. So I found this paper from Christophe's group where they looked at MLD of tithiocone with TD-MAT and ethylene glycol. That's this configuration, and also this other precursor I forgot the name of, but it has 3 functional groups. And here for this ethylene glycol case, they found that at some point the growth stops. And the explanation I read in this paper is that something like this happens. So at some point, you have these double reactions, and then the surface becomes unreactive for more precursor molecule absorption. So the fact that the reaction stops here tells me that this might be a good starting point for using these molecules as an inhibitor for selective deposition. Do you think this would work? Are there any limitations we have to think about?
But it's not reacted there forever. It still can be flexible and react with the second, like with the ligand that you're going to use for the deposition.
Yeah.
Like there is a probability that it will react with ethylene glycol.
Yeah.
Because those bonds are not fixed forever.
Yeah. So I think that it might be like a little bit of a dynamic system. The other thing is that of course only works if all of them react like this. So if like a fraction reacts in the monodentate configuration with the reactive group pointing up, then of course that's a site where your precursor can absorb. So then you're lost and you lose your selectivity. But on the other hand, I'm kind of surprised that this really stops. If it's, why does it work? Well, so this is not what you want if you want to do MLD, but why does it stop that well? It kind of, I think it's an interesting system to look into, but yeah. So 3 options. But the bottom line again is that with the toolbox you're working with MLD, some of these molecules can be useful also for other technologies. And actually this is some of the inspiration for some of the work that we're currently doing. So far I talked about 2 approaches for getting selectivity. So I talked about selective functionalization of the non-growth area, and I talked about 2 different ways of doing that. So you can do functionalization prior to your deposition using self-assembled monolayers, or maybe you can do it every cycle with these inhibitor molecules. And then before that I talked about selective precursor adsorption. There's one thing missing, and that's selective co-reactant absorption, if you consider that the ALD process has 2 different steps. But that's something that also has been explored, mostly for area-selective ALD of metals, so metal on metal deposition. So let's look at an example. So this is about area-selective ALD of platinum. So for platinum ALD, we typically use this ALD process. So you have the cyclopentadienyl precursor and oxygen gas. Typically you do this at a few hundred degrees, and I understood that this mechanism was partly discussed yesterday already. But the bottom line is that once you have a material, then this is of course you have to consider that this is a catalytic material. So it has, for example, catalytic activity for the dissociation of the co-reactant. So if you come in with molecular oxygen and it dissociates on the surface, and you have chem-salt oxygen. And it's important that the chem-salt oxygen is more reactive as compared to molecular oxygen. Then, so this is then the full mechanism. So basically, once you make chem-salt oxygen, then it can react with the precursor ligands in combustion-like reactions. So you basically burn off your ligands from the surface, and that's how you get deposition. This is how it works on a platinum surface. But for certain conditions, if you start with an oxide substrate, then this oxide substrate doesn't have the catalytic activity for dissociation of oxygen. So then your precursor may adsorb on the surface, but the molecular oxygen is less reactive than these oxygen atoms. That means that this reaction doesn't proceed, and in that way you can make the growth selective. And this is something that especially has been explored for the synthesis of nanoparticles. I showed you also this in the beginning. So this is metal on metal deposition. And here you can, for example, make ruthenium on palladium or ruthenium on palladium core shell nanoparticles by using the fact that these metals dissociate either oxygen or hydrogen as the co-reactant. Yeah. And this works for metals, but this is to briefly show that this can also work for some metal oxides. So by using the same catalytic activity of a noble metal, you can also, for example, grow iron oxide selectively with platinum. We'll skip this. And then basically we have three main approaches for making a process selective. So it's functionalization, using self-SAM monolayers or in ABC type cycles. It's precursor adsorption, or it's co-reactant adsorption. And then I come to the last part. So maybe first, are there some questions on this second part? Everything clear, kind of? Okay. So the last part is about the challenges that we're currently facing in this field. And one of them is that it is generally very difficult to achieve a high selectivity. And with selectivity we mean the difference in how much deposition we get on the growth and the non-growth area. So what we would like to have is like perfect selectivity where we only get deposition where we want it. But in practice there are always defects and impurities on your non-growth area. And these may be sites where the growth can start. Well, think about the self-SAM monolayer. If you don't weigh the full data, you might have some pinholes in the self-SAM monolayer, and you can have initiation of deposition there. So this is one of the main challenges, is that it's difficult to grow with a high selectivity. And that basically translates in that you can maybe do 1 or 2 nanometer selective deposition, but in practice, you may want to have 5 or 10. So then you have to do something about it to improve that. So the main solution for this is to combine area-selective ALD with selective etching. And luckily, currently there's a lot of development going on in atomic layer etching, so we can make use of that. So we can combine area-selective ALD with etching to improve the selectivity. So how does that work? The starting point is that we have some difference in growth or nucleation on the growth and the non-growth area. So maybe we have already layer by layer growth on this surface, but we may make some islands or individual atoms on the non-growth area. And then what we can do is, after a certain number of cycles, do an etching step. This should be selective etching in the sense that we etch only this red material and not the underlying substrate material. Unfortunately, such an ALD process is often not area selective, which means that you also remove some material here from the top. However, as long as you deposit more than what you etch, this might not be a big problem. And then the nice thing is that you can do this over and over again until you reach the desired thickness. So in this way we can make thicker films in an area selective manner with a good selectivity. I would like to show a brief example. So this is about area-selective ALD of ruthenium. So here we aim for a metal-on-metal deposition. So we use this ALD process. And here you see deposition on ruthenium and on silicon oxide. And what you can learn from this is that if you go to lower temperatures, then we get quite a difference in growth rate. And we can make use of that as a starting point for having a selective deposition process. But it's not good enough. We also get some deposition here. So what we do is we combine this with an etching cycle. And here in this case, we use an oxygen plasma for etching. So with an oxygen plasma, you can etch ruthenium, then you make ruthenium 04 as a volatile product. And that way you can remove the material. So what we basically do is we combine ALD cycles with etching cycles in what we then refer to as a supercycled recipe. So we switch back and forth between deposition and etching. And so this is a typical result. So here we're looking at the non-growth area. So we don't want to grow on the silicon oxide. And what you see is here we do an etching cycle after every 100 ALD cycles. And what you see is that, well, here in this experiment, we varied the oxygen plasma exposure time, so the duration of the etching step. And what you see is that for 5 seconds, we remove some of the ruthenium on the silicon oxide, but we still effectively have growth. But if we then extend it to 15 or 13 seconds, then we etch back completely to 0. Or in other words, we can completely remove the ruthenium from the non-growth area, and in that way improve the selectivity. And here you can see the results. This is top view SEM. So this is how it looks like if you don't do any etching, which is basically completely covered with ruthenium. And here you see that we get quite a good selectivity if we do this etching step after every 100 ALD cycles. We'll skip this because I would like to, in the last 10 minutes, discuss the last challenge. And also there I want to see if we can make use of MLD technology. So one of the challenges is that ALD leads to isotropic deposition, which means that if you use, for example, a SAM monolayer, that monolayer has a thickness of maybe like 2 nanometers. So if you grow a film that is thicker than this 2 nanometers, then at some point you'll get lateral broadening. And you can imagine that if we're talking about 7 nanometer technology, we want to make small features, this is not what we want. We don't want to make that it grows also in laterally. Another thing is that if you use self-assembled monolayers and you use a nanostructured surface, then well, this monolayer is not going to be perfect around corners. So these can also be sites where the growth starts. So, but let's look at this first challenge, the lateral broadening, which is, I think, one of the main challenges in this field. So this is a study from the group of Marit Carpino where they found a nice solution to this. So here they performed a deposition on the wings of a cicada insect. And then what, well, basically these wings contain holes, and the sidewall of this hole has a waxy layer. And if you then perform, for example, zinc oxide ALD on that, then you grow on the bottom, but not on this, which means that if you do the deposition, then you get pillars where the height is larger than the width. Or in other words, it seems that here you don't have this lateral broadening. And the reason for that is that you have, in addition to this chemical difference between the bottom and the sidewall, you also have like a structure, topographical difference that steers the deposition or limits the deposition in lateral direction. So the question is, can we think about something with MLD technology to eliminate this? Last discussion before the break. Maybe we can do this one together. Any ideas? So the limitation is basically the thickness of the self-assembled monolayer. So it's only like 2 nanometers or 1.5. So what you could do, I was thinking about something like this. So maybe do like a few MLD cycles, cap it off with a monofunctional precursor, what we discussed before. And then if you then grow, it might happen only here, and then it might not laterally broaden. Do you think this will work? As we discussed before, I expect you to be more an expert in MLD technology than I am. So, yeah?
I mean, in one of the last talks yesterday, we considered that MLD stackings of a certain length tend to tilt. This is something we should certainly keep in mind.
Yeah. Indeed.
This might then hinder very selective further at the bottom.
Yeah. That's also what I was thinking of. So this is a recent study where they found that you have typically a certain angle, and that also actually it's often not like a perfect layer with nice ordering, but you do have also some crystallinity in the vertical direction, etc. Yeah?
something that we could do to address that is choosing precursors that, for example, are really, really rigid and so don't have very long side chains, but rather systems that tend to undergo high stacking, for example.
Yeah.
That might help.
Yeah. So that was my follow-up question.
Yeah.
So I know that this happens, but there are other chemistries where you can prevent it. Because if you have like very rigid molecules, then this could be extremely interesting to see if this works. So if you have any suggestions for that, let me know. It's maybe something to think about later on if you learn a little bit more about MLD chemistry. Then I come at the end, and basically we'll skip over this, but this is the summary. So throughout the story I gave a few different motivations for why area-selective ALD is interesting. I talked about the elimination of compatibility issues. Think about the carbon nanotube field effect transistor. I talked about self-aligned fabrication. There we talked about the interconnect. And I talked about the controlled synthesis of complex nanostructure. Actually, I didn't really point it out, but for example, the core shell nanoparticle is such an example where by doing this, you can make core shell nanoparticles with other techniques, but ALD gives you the opportunity to actually tune the thickness of the shell. So this is gives some additional opportunities. Then at the beginning I talked about different approaches for patterning based on ALD. So it's area activation or area deactivation. And then in the middle part it was about different approaches for how you can make a process selective. So then it's functionalization, selective precursor adsorption, or selective co-reactant adsorption. And then the last thing is that the two main challenges is to achieve a high selectivity, but also to do something about this lateral broadening, because I think this is one of the main challenges here. That's it. Thank you.
Thanks a lot for the very inspiring talk. Any questions?
So in area-selective ALD, it's a lot about nucleation, and when you study nucleation, a lot depends on your starting surface,
Yeah.
your substrate.
Yeah.
And maybe you can comment on this and give some tricks also towards the students on how to ensure as much as possible that when you compare different experiments, that the surface that you used in the beginning is more or less the same.
Yeah.
Because
Yeah, so
subtle differences will have a lot of.
I think this is a very important point. So that also means that if you look at the nucleation behavior, actually one of the first things you have to do is, am I sure that my surface is clean? Do I have to maybe do some additional pre-treatments to clean it up, or to maybe functionalize it with more hydroxyl groups or something, or even less, something like that. That's one thing. I think also that's something that's a little bit lacking in the field. We have to do more about understanding whether these pre-treatments are enough, whether we have the surface that we think we need. So I think there is an important challenge there to, for example, use in situ techniques to characterize the surface before you start the growth. So
And like in the example that you showed where you group silicon oxide on different oxides, there these oxides were they grown in situ also with ALD, and then you continue with your process, or have they been exposed to air?
Yeah, so there actually most of them were grown in situ, but then you come into another problem. If you use the same reactor for preparing the surface as where you do your deposition, then your wall changes. So what we typically did there is we first grow the layer, then move the sample to the load lock. So this was an Oxford Instrument system where we had the opportunity to do that. Then coat the wall with silicon oxide, condition the wall, then move it back, and without breaking the vacuum, doing it like that. But indeed, so that is one way. I think that this is actually one of the nicer way of doing it, to prepare it in situ without breaking vacuum. But in principle, you cannot do that for most of it. most of the experiments. So then it becomes even more important to really make sure that what you have is what you expect.
There will also be more opportunity to discuss over lunch.
Yeah.
Thank you very much.
Okay.